we formulated a theorem on the last normal lecture which we had. So which said the following. Oops. Vector spaces are isomorphic, which means that you can create isomorphism between them if and only if they have the same dimension. So in order to prove this theorem, so we split the proof into two parts. The first will be lemma, which says the following: if spaces are isomorphic, which means that you can create isomorphism between them, then they have the same dimension. Pay attention that this is just half of the proof, right? Because of the theorem, because here we are saying if and only if. So essentially, it means that here we have two statements. One is vector spaces are isomorphic if they have the same dimension. This is the first proof, and the first statement. And second statement is if vector spaces have the same dimension, they are isomorphic. So, because if and only if, it's you need to prove this statement in both directions. So this is first direction, this one. Okay, so proof here is simple. So, and based on the following fact, we will just consider isomorphism between two vector spaces. And then I will show that if B, which consists of V1, V2, Vn, is a basis for vector space V capital, then D, which is F, my isomorphism applied to V1, F applied to V2, so on to F applied to Vn, is a basis for vector space W. So essentially, then I'm getting that number of vectors in the basis is the same, and that's it. So essentially, I'm getting that dimension is the same. For isomorphic spaces, dimension is the same. In other words, number of vectors in the basis. Okay, so let us do this. Let us consider any vector V belonging to the vector space V capital. Then V can be represented as alpha 1 V1, alpha 2 V2, alpha n Vn. Where why? Because B is a basis for V capital, right? So it means that my any vector from V can be represented as a linear combination of vectors of the basis. Okay, great. Now, let me consider W for any W belonging to the vector space W capital, the image of V. So because isomorphism is onto, right? So there exists V belonging to the vector space V capital such that f of V is W, right? So in other words, for every vector in the resulting vector space, I can find a vector which can be mapped into this vector W. Okay, but now for this vector, this is true, so I can represent it as a linear combination of vectors of the basis. Then I'm getting that this any vector W has to be f applied to this. But then using this preservation of structure, so I'm getting that my vector W can be represented through the linear combination of images of the vectors of the basis in V capital, right? So in other words, I got that W is spanned by this. Okay, so in order to show that this is a basis, all I need to do, I need to show linear independence, right? Okay, let us do this. So for that, let us consider C1 F V1 linear combination. And we are saying that this is zero vector in the W space. So in order to show that they are linearly independent, I need to show that this is possible only when C1, C2, and so on till Cn are equal to 0, right? Okay, so again, using preservation of structure, I'm getting that this is equal to 0. But I know that isomorphism maps always maps 0 vector into 0 vector, and this is one-to-one correspondence. So then I'm getting the following. Here I can say that this, because it's one-to-one correspondence, I'm getting that this is equal to 0 vector. But these vectors, they form a basis in V capital, right? Then from here, I'm getting that all C's are equal to 0. So it means that these vectors are linearly independent. So I got that vectors span the vector space. These vectors, they span the vector space and they are linearly independent. It means they form a basis. Number of vectors in the basis is exactly n, right? The same as a number of the vectors in the basis for original vector space. That's it. So I got that dimension. Yeah, and also we remember that I have proven that inverse for the isomorphism is isomorphism as well, right? So as a result, I can start from vectors from the basis here, right? And do exactly what I've just done in order to show that the number of vectors in the basis in the vector space V capital will be the same. So I have shown that dimension is the same for isomorphic spaces. Okay, end of the proof. And the second part of the theorem is the following: that so in this direction now, lemma. If spaces have the same dimension, they are isomorphic. Okay, we need here to remember, so okay, proof. Here we need to remember that I have proven that isomorphism of isomorphism is also isomorphism, so transitivity. And okay, here it's very simple. So if I consider V, right, so arbitrary vector in my original domain V capital, so belongs to V capital. So then there exists a basis, and I can represent it as like that, right? But then I can say that I use representation with respect to this basis and form a column vector so which belongs to Rn, right? So I can form a column vector, so one-to-one correspondence onto, so it's easy to prove that this is isomorphism. But then what I have shown that, okay, so my V has these vectors as a basis, right? So it has dimension n, number of vectors in the basis n. So I have shown that it's isomorphic to Rn, right? Okay, after that, so you see, I started from the arbitrary vector space, and I have shown that it's isomorphic to Rn, n-dimensional vector space, and I have shown that it's isomorphic to Rn. But then now I can take, it means that I can take any n-dimensional vector space, and it will be, let's say, W. So, and we consider vector W such that it's beta 1, also n-dimensional. And there is a corresponding basis. And also it will be isomorphic to Rn because I can create this isomorphism, one-to-one correspondence. Okay, it's you can check. It's very easy to check that it preserves structure and so on. So I have shown that two arbitrary vector spaces with the same dimension, they both isomorphic to Rn. But then I know what that I can consider inverse transformation, inverse map, which also is isomorphism, as I have shown before, right? And then I see that by transitivity, because V is isomorphic to Rn, and if I consider this inverse map, which is also isomorphism, I will get W. So by transitivity, I'm getting that V is isomorphic to W, right? Because they both isomorphic to Rn. So to just cone vectors and n-dimensional cone vectors. That's it. So it means that two arbitrary vector spaces with the same dimension are isomorphic to each other. And I just gave a recipe how to create isomorphism between them. Is it clear or not? Any questions? Okay. And immediately from here, follows a corollary. Pretty obvious one. That each finite dimensional vector space is isomorphic to one and only one Rns, because each finite dimensional vector space has some dimension, let's say n, and then it will be isomorphic to corresponding Rn. Column vector with n entries. So example, let us consider 2x2 real matrices. So we have A, B, C, D, right? So we can consider always natural basis. Could you please tell me what is the dimension of this space?
4.
4.
Hmm?
4.
4.
4, exactly. So it means that R2x2 is isomorphic to R4, right? For example, I can consider the following isomorphism. Right? That's simple. Or, by the way, you can consider different isomorphism. Right? Which one?
Would a different isomorphism just be reversing the arrow? So one is isomorphic to the other.
So Yeah, so you see, for example, you can exchange these two basis vectors, right? So for example, you can consider like that. So A, C, B, D. It's also isomorphism, right? Or you can have a look at your problem number 6 in the exam, where we exactly created isomorphism between R2 by 2 and R4. Right or not? So we have shown, so there was a different formula. So we use there the following formula. A plus B, A plus B plus C, A plus B plus C plus D. And we have shown that it's also isomorphism. But this is nothing else but vector from R4, right? So isomorphism is not unique. But if you start from 4-dimensional vector space, isomorphism can bring you only to the R4. I mean, to another 4-dimensional space. You cannot get in 5-dimensional space or 3-dimensional space. Exactly the same dimension. Is it clear or not? Any questions? Okay. Now, so once again, what is isomorphism? So first requirement is 1-to-1 and 1-to. Second, preserves structure, right? Can we use any of these requirements? Okay, so of course we can ease any of them. The question is whether we get anything useful as a result. Because, okay, you can get something, but it will be completely useless. So, or in some cases it's useful, but has pretty narrow range of applicability. For example, some nonlinear maps, right? Okay. Really, so if you remember, so we use this condition a lot, right? This preservation of structure and so on. So we use it a lot. So let us suppose that it stays. So why it's important? Because you remember we need to have so if we have a vector space, then under if our map preserves structure, so we will get something at least very close to the vector space, right? Again. So, but if it's not 1-to-1 and onto, so if we forget about this, so take it away. It appears that we are getting homomorphism or a linear map, which is extremely useful thing. So in a sense, it's not so rigid as isomorphism. As a result, it has way wider range of applicability. And so as you will see, a lot of things, a lot of different problems, physical or, I mean, whatever kind of problems from engineering and science can be formulated as through the homomorphisms. Okay, definition. a function between vector spaces that preserves addition so for any v1 v2 belonging to V, the following is true: h of v1 plus v2 equals to h of v1 plus h of v2. And scalar multiplication, or it's better to write it multiplication by the scalar, so why I prefer to say multiplication by the scalar, because in many books dot product is called scalar multiplication, so it's different, a little bit different story. So for any V belonging to V and any R, which is a real number, the following is true. So such a function is a homomorphism or linear map. Okay, so we have shown before that instead of checking these two conditions, first this, then this, we can check just one. But more complex. So, and this is equivalent to two of these, right? So if this is true, then both of these are true, because you just, for the first one, you choose alpha 1 and alpha 2 equal to 1, and then you're getting this. And for this one, you choose alpha 1 equals to R, and alpha 2 equals to 0, and you're getting exactly this. And vice versa, I have shown that if this is true and this is true, then you can show that this condition is also true. Okay, so examples. Okay, the very simple example. We consider x, y, z, right? And we map to just the real number, right? So from R3 to R1. Obviously, this is not one-to-one map, right? Because, for example, if I consider 3, real number 3, how can I make it? I can make it as 1 plus 1 plus 1. Or I can make it as 2 plus 1 plus 0. or I can make it as 3 plus 0 plus 0. And really, I can do this in infinitely many ways, right? So how to show that there are infinitely many ways? Because if you just write this, so you obviously know that there are three variables, right? 2 free variables, right? So infinitely many solutions. So in other words, if I take, yeah. So for example, I can just, if I set z, for example, then I know that any x and y, sum of each will give me 3 minus z, will satisfy this equation, right? So that's it. Okay, so great. This is an example. Another example is a projection map. For example, if I start x, y, z, which belongs to R3, right? So have a look. Right? So, and here is my vector x, y, z. So I can map it into x, y, which belongs to R2. Just like that. So I'm meeting z. So once again, 2 different dimensions. And yeah, so this is a projection map, which is used in many applications. Okay, so to show that this one is a homomorphism is very easy. So let me do it for this one. So first, I need to consider, let me call this map pi. Let me consider map pi of x1, y1, z1, 2 arbitrary vectors, and x2, y2, z2. So sum of 2 arbitrary vectors. So I know that it will be x1 plus x2, y1 plus y2, z1 plus z2. So I'm getting that it's x1 plus x2 y1 plus y2. But I can write it as which is pi y2 x1, y1 z1, map pi applied to x2, y2, z2, right? So we have shown that there is closure with respect to addition, preservation of addition. And now R, x, y, z, Rx, Ry, Rz, Rx, Ry, so end of the proof that structure is preserved. Is it clear or not how to do this? Any questions? Okay.
Sorry.
Yeah. Yeah. Go ahead.
I have a question about so I don't quite understand how we correlated the two if they are not in the same like R dimension.
So, for example, yeah, so they are not the same dimension, but I do not require it. So there is no requirement for this map to be one-to-one and onto. The only requirement is that this map has to preserve structure. Okay, very simple example. Let us consider P3, A3x cubed plus A2x squared plus A1x plus A01, right? And let us consider M, okay, not M. R2 by 2. So essentially A11, A12, A21, A22. Really, let us make it simpler. So let us consider just R. And R will be nothing else but just A0. So essentially I'm taking A3x cubed plus A2x squared plus A1x plus A0 multiplied by 1. And so element of polynomials of degree 3. And I map it to just A0, which is just the real number, right? So 4-dimensional space, 1-dimensional space. Okay, so let us prove that it preserves structure. So essentially, let me consider second polynomial and map is to B0, this polynomial. So if I will consider, so this map which F which maps P3 to R. So F polynomial 1, polynomial 2, polynomial 1 plus polynomial 2 will be F of A3 plus B3 x cubed plus A2 plus B2 x squared plus A1 plus B1 x plus A0 plus B0 1. But then this I know will be just this coefficient A0 plus B0, right? But this correspondingly I can write as F B1 plus F B2, right? A0 B0. So I have preservation of a sum, and now all I need to show is preservation with respect to the multiplication by the scalar. So it's RA3 x cubed plus RA2 x squared plus RA1 x plus RA0 1. Okay, result of application of the function is this coefficient, right? But this is equal to this, right? So I have preservation of multiplication by the scalar. So is it clear or not how I do this? So once again, I ease the requirements, so I do not have one-to-one requirement anymore. Okay.
Okay, yeah. So you're pretty much just showing that it can map. Oh, I think I understand. Yeah.
Yeah, perfect.